So this is Spring Top 24 here. I'm going to be reacting to Beyond Infinity Comprehension. Yeah, it's a video about comparing things that are in the real life in the universe and stuff. Yeah, this video I actually watched it like in my childhood. I actually got used to watching it. Now I haven't watched this for a long time and I still remember it. And it's still just like so good, bro. Like now that I'm smarter, I'm ready to analyze all this stuff around here now. Pretty smart in math. This contains all this math something now. I've already learned a lot, and yeah. Wait, when I first watched it, I was like, was 5 or 6 years old, and now I'm 12 years old. I'm ready to analyze all this stuff. There's gonna be many pauses here, but I hope you understand. Uh,
When a shopping cart
I
smashed
don't
my
know why
midlife,
there's an
we
ad, but
worried we'd have
let's
to fight
just
to
wait.
get paid for such a small claim.
And life would revolve around the shopping cart.
No, this is skip. Oh, this skip. This is skip. This is skip. And you only live once. Yes, you only have one life. You can't have two more lives. Ooh, that's cosmic. Yes, that's also basic. 16 line companies who are over $100 million. 193 companies in the UN members. Now, I would argue here that it's not exactly 365 days. First, we have to consider leap years, which have an additional one day, and this usually appears in February. On the February 29th is a leap day, which adds one more to 365, which would be 366. This one says in a non-leap year, but if it didn't include that, it would have to say it would. But if it didn't, but if it didn't mention, if it didn't mention in a non-leap year, yes, there would be 366. But because it's said in a non-leap year, that's totally fine. 890 a Pokemon. Oh my God. Oh, almost 3,000 just for under. From the 9/11 attacks. What's 9/11? I don't know. 1,000. Wait, I've heard this. Wait, Jeopardy? Jeopardy? As of 2019. Bro, wait. I thought One Piece was the. Wait, um. Wait, how did this have so much episodes? Wait, I used to remember an episode that has over 1,000 episodes. That was One Piece. But Jeopardy, 8,000 episodes? Is that really watchable? Dude, that's crazy, bro. As of 2019, though. So, wait. Was it watchable, though? 30,000 numbers daily average. Oh, 30,000 games. Wait, what is there? Oh, there's a lot of games. I can't even see what. 50,000 aircrafts on Earth. Oh my God. What is this? What is this? Oh. Oh, wait, this is words. Wait, there are words. This is words. And, they're all blurred out, but I can tell you that it's worse. It's got bankrupt, man, I can't even read it because, yeah, because there's 172,000 English words. I'm wondering what this is. Pause. Wait, oh, this is the movies! Is this the movies? Nah, it looks like it. This is the movies, right? I was right! Alright. 500,000 is crazy. Subscribe. Thank you, subscribe. Wait, is this some... Oh, number of subscribers. Wait, let me see. Oh, now he has 2.14 million. It's not the same. Unless... Oh, wait. Oh, this is 5 years ago. So so after 5 years later, he gained... Well, how much he gained? 390,000 more subscribers, approximately, because, yeah, it says 2.1 million. If you do the difference, you'll see. Oh, yeah, all these faces. But there's so many faces though. Yeah, there was people in New York City. Oh yeah, New York City is really popular. What is this? Oh, is this all this newspaper from Wikipedia? Yeah, this is from Wikipedia. I know that. Yeah. Oh, Wikipedia articles, 19 million. For, oh, 42 million heartbeats of one person in a whole year. Now let me ask you this. How many heartbeats are there in one person in a whole day? So you would have to do two of them because there's non-leap years and leap years. So you divide 42 million by 365 and 42 million by 366, which will give you, yeah, I don't have time to solve that. We're just gonna have to do long division on that. Oh, 170 million. Big Mac. How are there so many Big Mac? So many hamburgers, bro. Sold in 2019. Dude, I'm shocked. Dude, who even has a lot of these, bro? 1.2 billion. The human population on Earth as of 2019. Yes, because that was earlier. Because right now there is 8 billion, so increase. Right now there's approximately 8 billion. More Instagram photos than humans. Oh, 400 stars in our galaxy, the Milky Way galaxy. That's okay. How does Earth maintain 3 trillion trees on Earth? Like that's like literal crazy, bro. More trees than the stars in our galaxy. What's that? Messages. Bro, there's so much stuff. Physical money. Alright, what's that word again? Um, now we're just saying, now we're just saying that important stuff is turning into these trillions amounts, like 37 trillion physical money on Earth in circulation, UCD equivalent. Dude, if this included values, this would be much more because I see these signs of hundreds. Yeah, 100 total number of cells. Yeah, that's true because one single cell is literally extremely small, and it's still very small even under a microscope in a human body. Yes, as you can see. 1.2 quadrillion financial assets. Now on to exponents. So this is 10 to the 16th, which is 10 to the 10 quadrillion. That's great because since the Earth is huge and ants are really small, comparing those will give you an insane amount of ants. Yeah, 10 quadrillion. Insane. Actually, 2.6 of the heartbeats all humans in an entire year. So you have to multiply 8 billion and 365, or 8 billion and 366 if we include leap years. And yeah, 2.6 times 10 to the 17th would be 260 quadrillion. Yeah. Oh yeah, I forgot about that one too, cause a single grain of sand acts like a powder, so it's actually super extremely small. A grains of sand on an average sized beach, it's like so huge, bro. Insects on Earth, so there's more than ants. Wait a second. 3 by 3 Rubik's Cube combination possible? Oh, yeah, because, like, well, wait, what is this? 43 quintillion. Dude, what? What? Oh, 100 quintillion data bytes ever created by mankind. Oh, yeah, you have to consider what the size of Earth is to get the number of to get the number of grains of sand on Earth. Because earlier we saw there was 7.5 quintillion grains of sand in an average beach, and for Earth, you would have and for Earth, which is about 1,000 times larger, which is about 1,000 times larger, or maybe shorter than that, because of the multiplicative division difference. So yeah, you can see there's actually 1 sextillion grains of sand on Earth. Now remember, a grain of sand is extremely small. That when compared to Earth, it almost looks like it's just nothing. Basically smaller than an atom when comparing DNA base pairs. 600 sextillion, one more. Okay, stars in the observable 1 septillion, dude. Okay, atoms in your body, yeah. Yeah, because an atom is extremely small. It's like 1 to the nano. It's like a nanometer, I think. Yeah, so this is 5 nonillion. And now we got 3.4 undecillion, 7.4 quadrillion. Wait, 4 by 4 Rubik's cubes. So yeah, this is 7.4 what is that again? 7.4 quadrillion. 4 by 4 Rubik's cube combinations are possible. Bro, dude, there's no way this. Dude, oh wait, atoms on Earth, dude. What is that again? What's so 136 decillions atoms on Earth. Let's see what it is. Grams of observable. Now we're talking about math here. Planck time since the Big Bang. Now we're trying to keep track of 13.8 billion years of the universe's past of Planck time. Yeah, a Planck time is literally just extreme. A Planck time is literally just 10. It's literally just one. It's literally just 1 centidecillionth time. So multiplying that. So when multiplying these by exponents, well, yeah, total number of Planck time. Since the Big Bang. So a Planck time smallest of unit time is 10 to the negative 43. So what is that? What is that? Well, there's no name for that. Well, there's no standard name for that. Sorry about that. To fill in the cosmos. So now we're talking about grains of sand in the universe. And this is just 1 vigintillion. Dude. 52 card deck. 8. Hold up, let me go back for a second. Because there's something strange here. 8.1 times 8. 81 unvigintillion 52 card deck combinations possible. Huh? What? There's no and 4.2 dual vigintillion. Are you serious? Now we're talking about combinations of a 5 by 5 Rubik's Cube. And this is actually like 280 tres vigintillions. And what is that? 100 quintillions particles in an observable universe? Oh wait, that's standard. How did I not know that? Well, now I know that too. Many people have talked about this in their videos about particles in the observable universe. Man, over 100 quintillions. And 1 beta bytes. I would argue here that yes, this would be the heat death of the observable universe. All the heat is gone. It's going to reduce to absolute zero. You can check out that Melody Sheep video where I just watched the time lapse of the future, and you can see if you just memorize the time, you get a number about approximately one Google actually, but 10 to the 95. Yeah, that's like yeah, that is when. Oh wait, look. The last black hole evaporates and nothing else is left. So yeah, we just have we just have to wait 10 we just have to wait 10 um 100,000 times more of that this time to get this. Now remember, 100,000 is actually just 10 to the fifth. So when you multiply them with the same base, you add the exponents. 95 plus 5 is 100, which gives you Google. That's literally just 1 followed by 100 zeros. Oh wait, what? Did you know the word Google comes from the misspelling of the word Google? From the... Oh, this looks like we're getting into some misspellings here. Then why don't you just change it? Bruh. So there's one Google Answers and a Google. Wait, am I being... There's more chess games than this Google. What? So you're telling me there is one November trillion number of chess games that can be played differently. Xianji games that can be Novem quadrillion. Oh, you serious? 1.84. Do I have to read exponent here until we get to the... Oh, this one gonna take a while to do. Planck value is the smallest physical. This Planck val the Planck volume is the smallest physical unit in science. The length alone is over a trillion times smaller than an atom. Ooh, so we know an atom is about a nanometer. So if we just multiply by a trillion, it's 10 to 20, 10 to the 24th. So basically telling me there's no standard name for that, because what is this exponent here? So this is actually just 10 quintillion number of Planck volumes in the observable universe. Oh wait, now we're talking about volumes of the universe. That warps time. All right, so wait, 10 to the 2 to the 46. Wait, what is that? An octoquintillion Planck units of the observable universe in space-time since the Big Bang. Planck units. Wow, that's insane. Six older exponents. It's the example of a... Oh, that's actually an example of the days in a year. Well, not including leap years. Gold games that can be played differently. What? There's 100 deaths and... No. Actually... Yeah, no. It's actually... It's actually 100 Vichintins to centillion. Go games that can be played differently. Yeah. Oh wait, what? Wait a minute. Wait, QR codes that can be generated in 64 by 64 pi. 1002. So you telling me there's 100 Google Chime QR codes? Oh, it's because of these. It's because of these small black dots over there. Hold up a second. 33 by 33 Rubik's Cube. Who even solves the 33 by 33 Rubik's Cube? That's gotta be the most. Bruh. And 10 to the power of 4094. I don't even know. I don't got time to name that one. Well, actually, I do. Wait, let me figure this out. So, you're basically telling me that there's 100 milliliters quinquaginted to centillion 33 by 33 Rubik's Cube combinations possible? Dude, what the heck? No, that was hard too. Dang it. Oh, I'm not gonna, bro. There's another exponent. 10,500. You know what? I'm gonna quit. I'm gonna quit naming these. I don't have time. From 26 letters in the alphabet to 50. Since when did Chinese have 50,000 characters? Bro. Yeah, Chinese is definitely the hardest character. The hardest language to like do. 10 to the 206,000. Oh, we're getting closer to the sentence. Oh, well, yeah. Discovered in 1773, bro. That took almost 200 years. So wait, what you're telling me is... So what you're telling me is this was 253 years ago. "47 pages to print out. An Archimedes cattle problem." Wait, what kind of problem is that? Dude! 10 to the 1,830,000 books in a library of Babel? Dude. What about suffocation? And 10 to the 15 million HD images. Oh my god, bro. 10 to the 24,900,000 largest prime number. Oh, wait, so you're subtracting 1 from 2 to the 82,589,933. Largest prime number as of 2019. Wait, is 2019 special? Since when did 2019 become a special year? I was just young at that time. That was like 7 years ago. Just writing this phone number would take about 1,000 pages. Wait, who even figures out a number like this? Nah, this will take me about 4 years to... Or maybe it's 2 years. Wait. Power towers. 10 to the power 12. So it's 10 to the power of 1 trillion. So this is 10 to the power of 1 trillion. Now we're getting to power towers. Top of 10 to the 15 million. HD videos. Oh. And Boltzmann brain to randomly materialize. 10 to the 10 to the 69. These numbers are quickly getting bigger. At this point, it's not just exponential anymore. It's ultimately exponential. The growth of this is so insane. I mean, the top exponent is already getting so big, and we're already at a Googleplex, which is just 10 followed by Google zeros. That's literally impossible to write out. Look at all of that. Look, the exponent's already 100 zeros. So as a real value would be not enough. Yeah, like you can literally see here, it's already impossible to write it down. Wait. What? We're already into further power towers. We're now stepping into numbers that calculators can't even define. 10 to the 10 to the 10 to the 7, bro. Wait, universe and a multiverse. So how many multiverses are in a metaverse? Would it be larger? Okay, now it's just impossible to like explain it. 10 to the 10 to the 10 to the 10 to the 56. Possible ranges of every particle in our observable universe. Wait, they'll look like this. Wait, what universe are we talking about? What? 10 to the 10 to the 10 to 120? The universe resets itself via quantum fluctuations. Yeah. Oh my god, bro. What the heck? So fascinating. The exponent wouldn't even change a single bit if you try to change it, bro. The point reassurance time. Oh, now we got more power towers. So we got 10 to the 10 to the 10 to the 10 to 13. At this point, we're just entering tetration because Look at how many tens we're building here. Then the largest number in physics. Wait, there's an even larger number though, where the top exponent is just 10 times larger, but not 10 times larger the value, the googolplex to the power of googolplex. Wait, what do you mean? Here, admit it. As a child, when asked to say the biggest number you know, you probably said a googolplex to the power of googolplex. Well, it's probably this, but there's a number even larger than that, bruh. There's even more larger numbers to comprehend. Power towers of googolplex is crazy. Oh, now you have 1, 2, 3, 4, 5, 6 tens, and then an additional 50 to make it 7. To have 7 integers of a power tower. Now we got googolplex tetrated to 3, which is just googolplex raised to itself 3 times. Oh, now we get into some strong math stuff. Yeah, because tetration is just repeated exponentiation. Yeah, you can clearly see we're already into tetration, or we're about to leap forward even more because look at that 50 over there. I think we just skipped so many powers. Yeah. Hold. Oh. We just jumped straight into pentation. Oh my god. Oh, 3 to pentation to 3. Oh wait, this is actually easy to explain. So pentation is repeated tetration. Now we're stepping into some sort of hierarchy of operations. So here, pentation is repeated tetration. So 3 pentated to 3 is the same as 3 tetrated to 3 tetrated to 3. Notice that we still have to start from the top even with tetration. So 3 tetrated to 3 would be 3 to the power of 3 to the power of 3, which would be 3 to the 27, which as I did in my video, I already know, which would be 7.6 trillion approximately. Now you can see the reason here. I can see the reason here. There are 7.6 trillion threes in a power tower, which you can see it is 3 here. That's 7.6 trillion. That is what 3 pentated to 3 equals. And it's basically too hard to write it out, and it basically becomes impossible and solvable. And literally nobody can even solve it. Not even the fastest AI would know how to solve it. You basically can't. Yeah, you basically can't do that, bro. Not even I can do it, bro. Hold up. A googolplex times. So this is basically googolplex tetrated to itself, or googolplex pentated to 2. Oh, now we're talking about, like, right here. Powers of towers, googolplex. Yeah, googolplex is a number of googolplexes is a googolplex times, bro. Like, dude, this is so much, bro. Oh, wait, what's this? Oh, wait, what's this coming over here? 3 pentated to 4. Wait, what? Wait, let me see that again. Wait, it's far more bigger than a googolplex to the, yeah, it's far more bigger, bro. Numbers are literally getting bigger so much. It is so fast. The growth is so fast. We don't even know what to call it anymore. So 3 pentates 4. Just like I explained in the video, as pentation is repeated tetration, 3 pentated to 4 would be 3 tetrated to 3, tetrated to 3, tetrated to 3. Now for the top exponent, we already know that would equal 7.6 trillion. So that would mean in terms of the next tetration exponent would be 3 pentated to 3. So here's what I mean. Here's what I mean. This would be 3 pent. So here's what I mean. This would be a tower of 3s with 3 pentated to 3 amount of times. With 3 pentated to 3's amount of times. That's why there's a 4 here due to the top exponent. So this right here is just a single 3. This right here is 3 pentated to 2. This one is 3 pentated to 3, and this last one is like 3 pentated to 4. So now we're basically isolating the exponent into 4 types of power towers here. So yeah, you can see there's a 3 here because 3, there's 3 threes. Now this 3 will be 7.6 trillion. So that would mean this part right here would be 7.6 trillion threes, which is 3 pentated to 3, as I just reversed the operation earlier. That would mean in this larger area is 3 pentated to 4. is 3 pentages 4. That since we're adding another 3 in tetration. So this will be just 3 pentages 3 threes, which is equal to 3 pentages 4. Though these numbers are so massive, bro. Well, this is so that would mean this one is just 0 compared to this. It's like saying every number is 0 compared to the next number as we just go on. And now we just got 3 pentages of 5, which is basically just the same thing as I just explained earlier, but with 5 iterations. So this larger one here would be 3 pentages of 5, which is what it equals. Oh, we just jumped straight into hexation! Dude! So hexation here, this is actually an example of a Graham's number maker. We call this G1. So here, 3 hexated to 3 is the same. So let me say here, hexation is repeated pentation. So 3 hexated to 3 is equal to 3 pentated to 3 pentated to 3. So that would mean there would be a tower of tetration 3s of 3 pentated to 3 times, which is already too much. Which is already too much for a power tower. So basically, yeah, it's already impossible when we tried evaluating. Oh, we're now into the Graham's number creation. This is G2. This is G2. Now we're talking about a number of arrows in a linear way, in a linear dimension. So here, the number of arrows here is 3 hexated to 3, which we saw is G1. That would mean this expression will be equal to G2. The larger the integer beside the G, the more iterations we get over here. Yeah, so that's basically the Graham's number that's basically the function of Graham's number defined by Graham himself. Got 64. Oh, now we're already at Graham's number. Now you see the 64 over here? When you see the 64, we're now basically talking about 64 iterations, aka Graham's number should be G64. Ooh, yeah, this number is so big. Oh wait, a very famous large number coined in 1977. This number is the upper limit to the solution of a question of dimensional hypercubes. Now we're basically talking about 4D or 5D dimensions here. Yeah, you can clearly see. Yeah, that's why there's all these exclamation marks here, because there's no single object to define a number that's equivalent to all these massive numbers. G65. That's larger than Graham's number. Graham's number. Oh, now I have talking about Graham's number in iterations. Yeah, that's why this is G Graham's number. Or we can call this a plex something. Oh, iterations, small iterations, but this time this time it's plexed. But this time it's plexed with even more copies of G Graham's numbers, or Graham's number by itself. And this one F pi function pi 1. Oh, look at all these G's, and this is Graham's number. Now we're basically talking. Now we're basically talking about the growing higher. Now we're basically the fast growing hierarchy of Graham's number of these iterations of G's everywhere. This is Graham's number. That would mean there would be Graham's number of G's all the way down to this Graham's number, which would equal F function pi, function phi 1. Function phi 1. And now this more. Function phi 2 is the same. Function phi 2 is the same thing, but with more iterations of copies of this one right now. So now this iteration setup would be Graham's number of this iteration setup. So this is now we're basically talking about complexes of Graham's numbers with function phis of more iterations. The factor inside the number grows in this function phi, the more iterations we get. Now it's getting more and more complex. You can hardly see the numbers anymore. They're just blurries. Hold up a second. A function of phi 1. Ooh, phi 1s. There are so many functions. Oh wait, this is another example of iteration, but with function phi 1 here. Dude. Oh, it's more iterations. Tree 3! We reach a tree 3. That's oil. The solution to cross-cause tree theorem with 3 trees. It's so insane that it's not reachable using arithmetical transfinite recursion. So yeah, trees 3 is actually another famous number that is we all know it's way larger than the Graham's number. Now this is an example of the game of trees. So here, tree 1 we can only make one tree, so tree 1 would be 1. And so that would mean tree 2 would be 3 because we can have 2 trees, but we can only make 3 iterations. Tree 3 we can just keep on until we just reach this limit right over here. And you can see 187, 196 phees of iterations with function 1 here, which is equal to tree 3. So yeah, you can search on Google to find the rules of a game of trees because I actually forgot what they were. So yeah. We have tree 3. Oh. Three iterations of cheese. Now Graham's number is using is tree 3 itself as a combination to go more bigger numbers. Now we have more. Now we have more examples of trees here. Now we got tree 4, tree 5. Those are more negative numbers. No, actually, those are more. Those are more way bigger numbers that we still can't even comprehend. We can't comprehend the tree 3. So yeah, the first 2 trees are fine, tree 1 and tree 2, but the moment we step on the tree 3, it grows so large. Now we got tree of 3 and another iteration of tree 3s. Now we got iterations of tree 3s here. And once we do that, and once we continue on, we get SSCG3, which this function grows even faster than tree. So this is actually another example. This is actually another example of a function here. SSCG3, SSCG4, those more bigger numbers. SSCG5. Another iteration. Rails number. I already know that. It's defined in 2007 amidst big number duo. Yeah, so this is Rails number, which is already larger than any of these. Like what's out of the way, that's why it's the last here. The largest finite number ever defined. So now now that we hit Rails number, we're probably getting closer to the infinities here. So let's check. And here we are! Oh wait, countable infinity. So this is Aleph Nu, which is the countable infinity. Oh, we got this omega 0, which is Aleph Nu. We're now reaching to infinite ordinals. Oh, what do we got here? All rational numbers, Googleplex, Graham's number, Rails number, 1, 2, 3, 4, 5. Yeah, all these countings for 420 over 69, 8 over 7, 13 over 11. These rational fractions where these digits just go on forever. And 3.14926. That is an example of pi. And instead of all cardinals, now we're going to be stepping into infinity cardinals here, where it's not countable infinities anymore. It's uncountable infinities. So now we're basically stepping into a world of infinities here. So we're starting off Aleph Nu, which is just omega 0, which is this set of transfinite ordinals, and also a countable infinity here. So now this is a math for omega, which is an example of infinity. Now it's using the sum of normal numbers. And and if you keep going on, you'll eventually get into the multiplication of omegas and exponents of omegas. It just keeps getting larger. But in real math, those are all still infinities, just larger, just larger versions of one. And as you can see here, when this 0 changes to 1, it now becomes an uncountable infinity, because we already did the same operators. We already went to another cardinal infinity. Now we reach the uncountable infinity, which is omega 1, which is Aleph 1. So yeah, it's not countable infinity anymore. It's the uncountable infinity, where it's an even larger infinity of aleph. Replaceable uncountable infinity. Now we're getting iterations of towers. Well, not towers because now they're pointing downwards. So this is the aleph omega. Yeah, you can see the omega is actually a Greek symbol. You know that. The more iterations you do, the closer you get to the cardinals, which is epsilon. The replacement inaccessible infinity, epsilon null. This is the next stop after the first cardinal of infinity. The replacement of inaccessible infinity. Where now it's we do epsilon nu, we're going to do the next iteration. But there is something called epsilon omega, which is nowhere close as epsilon nu. You just basically keep going until you move on to the next cardinal. Now we're getting into a set of worlds where the next infinite cardinal takes you to the next step of the infinity cardinal. And as you can see, there are actually infinite steps of cardinals here. So this thing just gets fast. So the iteration just gets faster and faster. Now we call the character's ordinal, which you can see this is actually the zeta Greek symbol here, which is the indescribable infinity. Yeah, so this is zeta nu, and more. Now we're on to in predicative infinity. So this is the gamma. This is gamma nu, which is Pfefferman-Schutz ordinal. And we're reached to the end, which is absolute infinity. Now this is the main end for cardinals of infinity, but there's actually more cardinals of infinity. There's absolute infinity squared, absolute infinity tetrated to 2. There's even absolute infinity. There's actually a next cardinal of absolute infinity. There is absolute everything, transfinity, never, and more, and more and more, and more and more. So yeah, there is even more. But there's this one suspicious thing that we don't do, which is 1 divided by 0, which is larger than absolute infinity, which is larger than absolute infinity. And the reason why I mentioned this is because it's basically infinity, but an indeterminate, undefined expression we can think of. So yeah, as an indeterminate form for 1 divided by 0, this is nowhere close. This is nowhere near the true end of math integer numbers. And this takes us to the end of the video. Yeah, just basically it. I can't believe I talked so much here. Yeah, just because I've been way interested in maths here. Anyways, that's it for the video, and I hope you enjoy this.